Hello, everyone, and welcome to this seventh appointment of our 40 under 40 lecture series on combustion. It is a pleasure to have you and to have with us as a speaker, Professor Davide Laera from Polytechnic of Bari. I will give a short introduction to the speaker, and then I'll leave him the virtual floor. So Professor Davide Laera obtained his PhD in mechanical engineering in 2016 at the Polytechnic of Bari, Italy. In September 2016, he joined the Department of Mechanical Engineering at the Imperial College London as a postdoc, performing high-fidelity large eddy simulation of flame dynamics. In 2018, he moved to Fairfax in Toulouse, France, initially as a postdoc and then as a permanent member of the CFD group from January 2020. At Fairfax, he focused on decarbonized combustion, hydrogen and ammonia, two-phase flame, pressure gain combustion, and thermacoustic instabilities. Dr. Laera won the Marie Curie Individual Fellowship with his project Cleaner Flames on a large eddy simulation of combustion instabilities in 2018. And in 2021, with the H2O team, was awarded the prestigious Athos Joseph Fourier Prize for his research on hydrogen flames. In September 2022, he was appointed as associate professor at the Polytechnic of Bari, where he is responsible for numerical and experimental research on decarbonized combustion for a sustainable energy generation and transportation. Davide, it's a pleasure to have you here. And yes, I leave you the virtual floor. Take it away.
Thank you very much, Salvatore. Before starting sharing my screen, I would kindly thank you, Alessandro and Bart, for the invitation for this, for giving this seminar. So tell me if everything is all right. I'm sharing the screen. Do you see one screen? Yep. Everything's okay? Audio is okay?
So far, so good.
Perfect. So I think that we can start. So
yes.
Good morning, everyone. As Salvatore said, I mean, I'm going to present you 50 minutes of talk on the impact of hydrogen addition on the combustion dynamics and acoustic response of lean premixed, partial premixed flame in gas turbine combustors. So briefly, we are going to talk about thermacoustics today. I don't think that I have to really tell you why nowadays we are talking about hydrogen combustion. If we see the plots here on the prediction of the emission of greenhouse gases that you can easily find online with a focus on aviation or global emission, you can clearly see that if we want to meet the carbon neutrality European target by 2050, we definitely need a change of paradigm in combustion systems. We need really to reach the carbon neutrality, and one way to do that is to move to a carbon neutral fuel such as hydrogen. It is considered nowadays one of the most promising solutions to do that. The problem is that if we compare the thermochemical properties of hydrogen with classic hydrocarbons that we use in gas turbine systems, such as methane or kerosene, what we can clearly see is that hydrogen has completely different properties. In particular, hydrogen is characterized by high flammability limits, higher chemical reactivity, so this means basically higher flame speed and low density. So this fact introduced a technology challenge. Hydrogen is not a drop-in solution. For people like me that have spent all this career doing modeling and doing simulation, the fact that we want to modify the fuel and use hydrogen in a combustion system will also introduce a modeling challenge. So new models are required to be developed in order to have reliable predictions. So in general, hydrogen is not a drop-in solution. So what will be the impact of an engine if you use it? Definitely, we are going to have modification in the flame shape, thermal load, emissions. We need to rethink of ignition problems, LBO or flashback, and also some instabilities problems of the flame, such as thermacoustic and intrinsic instabilities. Of all these problems, the talk of today will focus on thermacoustic instabilities. So this is the outline of my presentation. In order, I will briefly do a theoretical recap on what are thermacoustic instabilities. It's a really peculiar problem of combustion system. Then I'm going to focus on the use of a large eddy simulation as predictive tools for thermacoustic instabilities. The focus here will be more on which are the challenges and what are the requirements for an LES to be a good predictive tool for combustion instabilities. I'm going to present you a couple of simulations that I performed when I was at Fairfax on two different test rigs, on the premixed combustor from DLR and the Miradas in MFT, where these two test rigs have not been operated with the pure hydrogen condition, but where hydrogen was added. And the focus will be on the impact on combustion dynamics of the adding of hydrogen. Then some final remarks and ongoing projects. So, thermacoustic instabilities. In order to explain thermacoustic instabilities, let's first consider a sketch of a gas turbine combustor. In a sketch of a gas turbine combustion, what you will have a plenum, an injector, a combustion chamber with a flame. Let's imagine that for some problems, we have heat release rate fluctuation, so an unsteady combustion process inside the combustion chamber. When you have heat release rate fluctuation, what will happen is that you will generate acoustic waves. These acoustic waves will propagate downstream and upstream of the combustor in the plenum and the combustion chamber, will encounter the outlet and the bonds of the combustion, and will be reflected back in the combustion zone. The acoustic wave here may directly or indirectly interact with the combustion process. Then new heat release rate fluctuation will be generated, and this system may self-sustain, leading to thermacoustic instabilities. Let's now have a focus on how the acoustic wave can interact with the combustion process. Here I'll talk about direct and indirect acoustic flame interaction. We can mention some of the mechanisms. For example, we can consider that the acoustic wave will impact the injection and the mixing system. For example, in a perfectly premixed flame, the presence of acoustic wave may lead to mass flow oscillation, which will result in oscillation of the heat release rate. For a perfectly premixed or technically premixed flame where air and fuel are injected separately, the presence of acoustic wave may lead to fluctuation of fuel and air mass flux, generating equivalence ratio fluctuation, which, as you may know very well, will lead to, again, to heat release rate fluctuation. In a system where we have a spray, so when we operate with liquid fuels, what may happen is that the acoustic waves may couple with the evaporation process of the liquid droplets and again generate heat release rate fluctuations. Today, I'm not talking about liquid fuel. Interested people can have a look of a couple of recent publications that we have performed on spray flames and thermacoustics. Here I put the reference. The acoustic waves can also interact directly with the flame itself, for example, leading to flame surface variation. That, as you all know very well, if you are proficient in combustion, this will lead to fluctuation of the heat release rates, or may couple also with the hydrodynamic fluctuation of the system, which may then interact with the flame, generating, for example, vortex and flame interaction, flame tip roll-up. Recently, another mechanism have been discovered leading to thermacoustic instabilities that basically it is not directly to the acoustic waves that are reflected by the combustor, but it is referred to as intrinsic thermacoustic flame instabilities. What is happening basically is that you may generate some thermacoustic instabilities of the flame even in a system where you have an echoic outlet, and that is because basically the loop of acoustic wave flames happens inside the flame itself. The acoustic waves that are generated by the flame will propagate upstream. They will encounter the injector, and they will be reflected directly back on the flame. This may generate some acoustic instability that do not depend on the geometry of the system, so that's why they have been called intrinsic instabilities. This phenomenon have been almost discovered at the same time by researchers from TU Eindhoven and from Munich. Interested people in this interesting thermacoustic instabilities may refer to a very, very thin lecture that has been presented by Professor Polifke that I have moderated during the combustion webinar organized by Georgia Tech. I leave you here the link of the recording, the YouTube link of the recording. And very recently, Dr. Silva from TU Munich have published a comprehensive review on such phenomena. In this talk, I'm not going to talk about intrinsic thermacoustic stabilities, but instead I'm going to talk about classic acoustic-driven one. Okay, some example. This is quite famous in the community. It's a fully premixed flame stabilized over a backward-facing step that undergoes instabilities. As you can see, this flame starts oscillate due to the coupling with the acoustic waves, and then until a flashback phenomena happens. So, in two lines, thermacoustic instabilities derive as a self-sustained oscillation arise by the coupling between a source of heat and acoustic waves. They are not new, okay? They are new since very long time. It has been already 30 years that we are studying them. So we begin to understand them. Of course, the level of knowledge of thermacoustic instabilities over the years has increased. But nowadays, the adding of new fuel, we change completely or partially the system. Definitely, they are not desiderable. That is because what are the arms of a combustion instabilities? Combustion instabilities is definitely a source of combustion noise, not the only one, but it's the most important one. They may generate high level of pressure fluctuation that will cause structural vibration, component failure, as you can see here, or they may lead also to phenomena, unwanted combustion instability phenomena such as flashback and blow-off. What happens if, so the question of today is what happens if now we add hydrogen in our system? During this talk, I'm going to present two configurations in which hydrogen, in both of them we have added hydrogen, but in a completely different manner. The first one is the very famous premixed combustor from DLR, where very recently Isaac Box and Jan Koch-Streter have performed some hydrogen testing campaign. In the premixed combustor, here the hydrogen has been added fully premixed with the methane upstream of the combustor. So basically, inside the combustor, the methane and hydrogen are injected upstream of the combustor, then mixing up and a partially premixed flame is stabilized inside the system. The second test leak the problem is that in the premixed combustor, and here I can show, as soon as hydrogen reaches in the combustion chamber, a thermacoustic mode is triggered, as you can see from this simulation. We're going to discuss about this later on in the presentation. The second test rig that I'm going to talk about is the Miradas test bench that has been designed, operated, and developed at EMFT in Toulouse in the framework of the Scirocco ERC project. Why it is interesting also to discuss about the Miradas test bench? This is because, differently from the premixed combustor, here hydrogen is not injected fully premixed with methane, but instead there is a pilot line or pure hydrogen, a really, really small quantity of hydrogen is injected at the base of the flame root through this pure hydrogen pilot line. So in this case, so hydrogen is not premixed and injected at the flame root. Here you can see about what happens at the flame when we pass from 0% of the hydrogen. So this is a pure methane case to a 10% of hydrogen at the flame root. If we now talk about instabilities, I have a video that I think that we can stop. So as you have seen, until we have an unstable flame when operated in pure methane, that is stabilized as soon as a little amount of hydrogen is injected at the flame root. So what you can see here is that in both test rigs, hydrogen has been added. In one case, hydrogen led to the triggering of instabilities. In this case, hydrogen helps the stabilization of the flame. So what is happening here? If we want to study this problem, and we want to study this problem from a numerical point of view, so a modeling point of view, it is a quite challenging problem. That is because thermacoustic instabilities, if you have correctly understood, it's a multi-physical problem. You have to deal with acoustics, fluid mechanics, combustion, dynamical system. Over the years, multiple approaches have been developed in order to study thermacoustic instabilities, and they can be grouped in two major groups. Are the acoustic approach, so we study the problem from the acoustic point of view. In an acoustic point of view, in an acoustic solver, where we can use 2D or 3D modeling, that's not important. The concept is the same. We solve the acoustics, and the flame inside these models is considered as an acoustic element. So it's only considered as a source of acoustic waves. On the other hand, we have compressible LES simulation that can capture all the physics that I've listed here. Of course, at the price of an higher computational cost. Today, we are not talking about these methods that was the objective of my PhD thesis in Polytechnic University of Bari, but we are going to focus more on how LES simulation can be used to study thermacoustic instabilities. All the simulations that I've performed today have been performed using the high-fidelity compressible solver AVVP that it's quite famous in the community. It's developed as Serfax, in which resolves the reactive, fully compressible Navier-Stokes equation with the high-order Taylor hierarchy scheme, and it's been used for all combustion problems, also to perform thermacoustic instability studies. Now, in a LOS solver, if we want to understand which are the requirements of an LES solver that are needed in order to perform such studies, the first thing that we need to deal with is how do we account inside the solver the chemical reactions, chemistry. Generally, we can classify the approach into groups: the flame generated manifold, so the tabulated approach, where chemical reactions are pre-computed, tabulated as a function, for example, a progress variable, and stored in tables that are recalled inside the system. This approach, codes using this approach are it's computationally cheap. That is because, I mean, you need to resolve only one more transported equation, the one of the progress variable and its variance. The problem is that when you generate and you will pre-compute the chemistry, you perform strong assumption. For example, in the combustion regime, when you add hydrogen, as for example, we will see in the Miradas combustor, we are going to face, for example, multiple combustion regime system where you have fusion and premixed flame. So this can be a drawback. And furthermore, you need to compute also to complex effects in order to consider complex effects such as heat transfer or stretch effects. These need to be computed in the tabulation that you perform. Another approach that is the one that you use in a VVP is finite chemistry approach. In a finite chemistry approach, basically you resolve directly the chemical reactions while computing the simulation. So the combustion regime, the enthalpy effect, the stretch effect are an output of the simulation. The problem is that since you have to add a transport equation for each species that you consider in your chemical scheme, you cannot use the tail scheme. You need to reduce the computation, the chemical scheme that you require. So, in order to perform blends, hydrogen, hydrocarbons, methane, in this case simulation, one possible approach is to use reduced scheme. As this is the scheme that has been used for the calculation that I'm going to present you today. Has been derived using the Surfax developed arcane tool. I leave here the references for interested persons. This scheme has been derived starting from the detailed polemic scheme developed by the CREC group in Polytechnic di Milano, and which comprises 159 species and more than 2,000 reactions. The reduced scheme at the end of the reduction process is a scheme that comprises 15 transporting species, 9 in QSS, and 138 reactions that has been validated from a range of premixed flame ranging from pure methane up to also pure hydrogen, but here we go to 20% of CH4 and 8% H2. The second point that you need is turbulent combustion modeling. That is because in a premixed flame, in order to achieve stability in a code, if you have a finite rate chemistry approach, you need to have points in order to sufficiently resolve the thickness of your premixed flame. The point is that when you add hydrogen, the thermal thickness of your flame shorter, so this may become computationally demanding. So you need a model. The model that we use is the very famous thickening flame model. And the thickening flame model basically uses some properties of premixed flame, which says that basically the laminar flame speed is conserved if you divide the press potential factor, so you divide your reaction rate by a factor f, and you multiply by your diffusion coefficient by the factor f, you conserve the laminar flame speed, and you thicken the flame of the same factor f. The problem is that an efficiency function needs to be introduced in order to capture correctly the flame turbulence interaction, because you thicken your flame, so the response of your flame to the turbulence will be modified. This model is really famous right now. It's been implemented in the multiple CFD codes, such as ELS2, OpenFOAM, Convergent. You can find it everywhere. As I said before, we may encounter also multi-regime combustion, so we need to fix also diffusion flames. Well, diffusion flames, from a computational point of view, are less demanding. That is because thickness of a diffusion flame will depend on the resolved velocity gradient on which you solve your diffusion flame. So this means what this means is that you don't need to thicken a diffusion flame because the flame will automatically adapt on your mesh. The problem is that the reaction rate will depend on the scalar dissipation rate. So an under-resolved diffusion flame will lead to error in your heat release rate. Solution is the one of either introduce a turbulent combustion modeling for diffusion flames or impose feature resolution. In the simulation that we're going to present today, we use the first approach. So basically, we detect the flame region using, for example, a Takeno sensor, and we apply the respective modeling, premixed flame on a model for diffusion, premixed flame respectively, and then we, of course, choose the data at our disposal to validate our simulation. When you're going to deal with hydrogen, you of course, need to take really careful attention on transport properties. We all know very well that hydrogen spaces diffuse very fast. They have hydrogen characterized by Lewis number that is of the order of 0304. So this means that you cannot do as you are used to do with the methane flame. So use U is equal 1 approach, but you, for example, need to account for differential diffusion of the species. For example, adapting a transport modeling of constant Lewis, but not unity, meaning that you use a single Prandtl number for your mixture and different Schmidt number that take into account the different molecular diffusion of each species. When you do so, and you have hydrogen and methane separated differently, so not premixed, injected separated, you need to be very careful. That is because if you take a 3-component mixtures as this one, and you plot the Prandtl properties, and for example, the Schmidt number of selected species like was done here for N2, what you can observe is that depending on the relative percentage of hydrogen and methane that you have locally, the properties of the mixture will change. So when tuning, as I said before, tuning your Prandtl number in order to match the correct value will work if methane and hydrogen are injected fully premixed. But if they are injected separated, the transport property will depend on the local composition. Here you have two options: either use a full complex transport properties in your code, of course at the price of extra computational effort, or you can, as we have done in this publication here, you can think of a simplified complex transport approach based on the mapping. So on mapping the value of Prandtl and Schmidt number of selected species as a function of local composition. The impact of this may be huge. For example, here are some results that show the variability, for example, of the Prandtl number in the Miradas combustor, where you have here hydrogen air, methane air, and the hydrogen is injected. As you can see, the variability of the Prandtl number is quite huge. The same we can see for the Schmidt of the N2, with a non-negligible impact on the stabilization of the flame. When you use a simplified complex transport properties, the flames stabilize more close to the stabilization. Once we have fixed the combustion modeling, now we need to talk about boundary condition. Generally, for LES or compressible solver, we use a non-reflective boundary condition that have been derived by this famous paper from Poinceau and Laera. When you don't want to deal with thermacoustics, what you do with non-reflective boundary condition is that basically you tune the parameters of your non-reflective boundary condition in order to be to guarantee an anechoic boundary condition, so to avoid reflections inside the computational domain and guarantee stability. When you want to study thermacoustic instabilities, you cannot do that because you need to have a reasonably correct acoustic impedance, because you need to capture correctly the acoustic of your system. So if you use non-reflective boundary condition and SCBC incompressible solver for self-sustained limit cycle calculation of thermacoustic instabilities, be careful on the value that you use on the relaxed coefficient, because, as has been proved in this publication from Rovancel et Poinceau and Faknikou, this will modify the acoustic impedance of the boundary condition. So we may modify the acoustics of your system, leading to wrong thermacoustic predictions. Another key point for LES is the thermal boundary condition. So as you may see, as you may know, for thermal boundary condition, we have multiple strategies. Okay, we can use adiabatic flame. This is wrong, so it should clearly be avoided. We can impose the wall temperature at the wall. So basically, we have measurements in configuration where we have measurement, we can directly impose the temperature at the wall. The problem is that generally you do not have measurements in all your configuration. So this will work only on limited operative points. Another possible solution of this problem is to use, instead of imposing temperature, you impose an heat resistance. So basically, with the heat resistance, you take into account the resistance of the process of the heat conduction, convection, and radiation. So you do not impose directly the temperature, but you impose the resistance at the wall. If you do the hypothesis that the heat resistance will not change with the temperature, what you will have a condition that does not depend on the specific operative condition at which you have derived it. Of course, the last hypothesis is to perform coupled conjugate intrastate calculation. And today I'm going to talk about this studies that we have performed using the last two approach. Let's start with the first one. In the framework of Walter Agostinelli PhD thesis, what we observed is that in the Belgian combustor, basically operated with pure methane, we had some measurements of the thermal boundary condition. The problem was that these measurements have performed in different operative conditions. For example, for the Belgian operated at 20 kilowatt, 30 kilowatt, 80 kilowatt. So we have performed simulation in the case at 20 kilowatt, but we had measurements of the temperature in the back plane and the center body, and we had tuned and computed the heat resistance for these two boundaries. Then we have performed the simulation in a 30 kilowatt point, where we had some measurement of the temperature measurements on the wall, and we have used this computation in order to compute the correct heat resistance to put in this boundary condition. Once we had that, we have applied the two resistance in a third case in which we had no measurements at all. The third case of the present study, the study that I'm going to present you today, and was the one operated by Meyer and by Box and Janko for the hydrogen campaign. As you can see, the application of the Thun thermal resistant led to a flame shape that is reasonably matched. Okay, there are some mismatches, for example, it's a little bit shorter with the one observed experimentally. Now, if you are not interested in thermacoustic instabilities, your study ends here. The problem is that we were interested in thermacoustic stability, so we had to see what was the impact of this thermal boundary on the system dynamics. What we observed was that when we imposed the heat resistance, a thermacoustic mode was triggered, and this thermacoustic mode was purely numerical. So during the experiment, they didn't measure any dynamics in this operating point. When we switched back to a CHT calculation, magically, the thermacoustic mode stabilized. So the takeaway message here for you is that in order to perform thermacoustic instability simulation with an LES, you need to be very careful of your combustion modeling or your boundary condition, also your thermal boundary condition, because a wrong modeling in these three fundamental aspects may lead to unphysical results and the triggering or stabilization of the thermacoustic modes only because of the model. This said, let's talk a little bit about physics. So the first case that I'm going to present is the premixed combustor. Here I'll report a list of articles in which basically all the results that I'm going to present you today have been published. The test campaign that has been performed at DLR basically consists of operating the premixed at 10 kilowatts and the equivalence ratio more or less 0.8 for 3 different quantity of hydrogen. 0%, the flame was stable, and it's the case that I shown before. Then the quantity of hydrogen has been a quantity of hydrogen of 20% in volume and up to 50% in volume have been injected. And the most important point in case is the last one, where as soon as hydrogen is injected inside the system, a strong thermacoustic mode has been observed. The computational domain used for this simulation it's here. I want to point it out just one thing. In order to correctly capture the acoustic impedance at the outlet of the system, a portion of the atmosphere was considered inside the computational domain. This allows us to put the outlet boundary condition on this boundary and not here. I'm not going to talk about this, but I mean, in order to reduce the computational cost required for this calculation, you can, optimize your computational mesh using some mesh refinement technique, as we have done here for the premixed case. We use static mesh refinement techniques. More information could be found in this publication for Dr. Agostinelli. Before talking about instabilities, of course, you need to be careful. You need to be sure to have a stable flame. So here you can see that we make full use of the really high quality data set that they have measured at DLR, where we used in order to validate our simulation. As you can see here, we had a perfect match of our velocity profile and also of our flame shape. When hydrogen is added, of course, flame gets shorter, more compact, and stabilized more close to the flame holder here, the central body. CHT simulation gave us the possibility also to account for and to account for the heating up of the central nodes here, due to the fact that the flame stabilized more closer to the flame holder, that reaches temperature up to 1200 K. As soon as hydrogen is injected, as I said before, a strong limit cycle has been observed during the experiment. Here are some experimental analysis. Analyzing the spectrum of the pressure signal and also the heat release signal, what you can see is that the limit cycle that is being triggered is a bimodal limit cycle characterized by two main frequencies, a frequency around 280 Hz, and this mode has been observed only in the pure methane dataset of the premixed of, for example, the studies of Meyer, and higher frequency mode at 470 Hz that has been properly observed only in this testing campaign with hydrogen. The first thing that we have done was to compute and to characterize these two modes. One thing that you can do in order to characterize the mode is to perform the acoustic simulation using, for example, an Helmholtz solver. Here we have been using a VSP, but I mean similar calculation can be done with all the Helmholtz solver that could be found online, for example, also multiphysics or in-house solver. What we have observed was that basically, the adding of the hydrogen inside the system will only slightly modify the temperature field. That is because the flame is more compact, stabilized more close to the system. So basically, you can see that in this outer recirculation zone, the temperature is higher. But the impact of this in the acoustic mode is very limited. That is because, I mean, the impact of temperature inside the acoustic, the sound speed is under square root, so the pure acoustic mode of the chamber are not impacted by the adding of the hydrogen, and two acoustic modes basically, which are the two around which instabilities have been observed, could be found in all of the three configurations. One mode at around 280 Hz, which is the so-called Helmholtz mode, and a second mode at 486 Hz, which is the first mode of the combustion chamber. So if the hydrogen does not change the acoustic of the system, it will definitely change the response of the flame. And the reason why adding hydrogen the system became unstable could be looked for in the response of the flame directly, and not in a modification of the system acoustics. LES simulation will be able to correctly predict the limit cycle, as you can see here. Basically, I will report an image of the pressure fluctuation that have been recorded in the plenum, in the combustion chamber, and also some oscillation that have been recorded of the heat release rate. And furthermore, I've extracted from this the flame shape at 5 different points during the cycle, and compare with them with what have been observed during the experiments. As you can see, a good match have been observed for the flame shape, from the flame shape, and LES simulation, of course, can be further explored in order to understand and better characterize the limit cycle. In particular, what you can see is that during the limit cycle, the length of the flame changes, and changes also the flame surface. The flame will be elongated and will be further pushed inside the system during the limit cycle. Also, the stabilization point of the flame on the center body the point at which this point is stabilized modifies during the limit cycle. It goes up and down and follow the movement of the flame. You can clearly see, but we are going to discuss that for further detail, some flapping oscillation of the jet, because the fuel here in the system is injected down here, and along the limit cycle, this jet is flapping following the oscillation, limit cycle oscillation, and this will lead to further pocket of fuel that are then convected inside the flame zone, leading to heat release rate oscillation, so that sustain the limit cycle. And also you can see a strong interaction of the flame surface with the vortex shaded by the injector at the injector plane and the injector exit, leading to variation of the flame surface due to flame roll-up mechanism. As I said before, the mode that we observed in the Kinsta is characterized by two frequencies. So we can use we can further exploit the LES using some projection techniques in order to extract the component of the two modes of the system. In particular, here we have used DMD analysis in order to extract the pressure fluctuation, heat release fluctuation, fuel fluctuation at the 280 Hz component, 486 component of the oscillation. In this plot, what we have plotted is the so-called Rayleigh index. The Rayleigh index is an index very famous in thermacoustics that basically compare the phase of the fluctuation of heat release rate and pressure fluctuations. A positive Rayleigh index means that the two fluctuations happen in phase, so the two oscillations are drive the instabilities. Otherwise, a negative value of the Rayleigh index means that the two oscillations happen out of phase. So this, in this point, basically, the oscillation operate to stabilize the instability. Of course, in an unstable flame, the zone driving the instabilities should be larger than the zone controlling the instabilities, damping the instabilities, and this is the case for both oscillations, for both modes, for both components of the oscillations. We have done the same also, so we have correlated also the fluctuation of the mass fraction of hydrogen with the fluctuation of mass fraction of pressure. This is because we wanted to check the zone where the oscillation of fuel happens in phase with the oscillation of pressure. And as you can see here from these results, in both cases, so in both modes, the oscillation is supported by equivalence ratio oscillations that happens in phase with the pressure oscillations in different zones. We can do the same also with vorticity, and what will happen is that a coherent distribution of vorticity pressure fluctuation has been observed only for the F2 modes. So this led us to our conclusion on this analysis was that in these bimodal modes that have been observed in the premixed combustor, both modes are supported by heat release rate fluctuation, but only the second mode is supported by the vorticity and pressure fluctuation correlation. So this means that the adding of hydrogen and the shorter of the flame changes the characteristic time of the flame that now correlates better with the vortex shaded at the edge of the injector, leading to the coupling of the second mode with the second mode. Moving on to the Miradas combustors, as we have done before, here you can find a series of articles in which the results that I'm going to show you today have been summarized. In the Miradas combustor, as we've done before, basically what happens is that injecting hydrogen here, we stabilize the system, as you can see from this stabilization map. Different from what we have done for the premixed, in the Miradas combustor, we didn't want to simulate a self-sustaining limit cycle, but we want to focus more on the flame. In particular, we wanted to compute what it is known in thermacoustic as the flame transfer function. The flame transfer function is not more than a response of the flame to acoustic fluctuation. So a modeling of the flame that correlates the heat release rate fluctuation of the flame with the upstream calculation. This mathematically traduced in the very famous N-tau model in time domain, or in the so-called frame transfer function in the frequency domain. So a complex function that is characterized by a gain and a phase. But what this says is that to the acoustic oscillation, the flame will respond with the heat release fluctuation that have a factor n with respect to the amplitude of the velocity fluctuation, and are different in phase with respect to the fluctuation of velocity fluctuation in one point of a phase f. To do so, what you can do in LES to compute this FTF is to consider your flame a stable condition, so you want to avoid self-sustained calculation and force the flame from the inlet with, for example, imposing some harmonic fluctuation at the inlet boundary condition. Experimentally and numerically, what have been observed in the Miradas is that this is again the phase of the Miradas FTF for the reference case without hydrogen, and this function is highly modified when we add hydrogen. For example, this is the case when we injected 10% of hydrogen. As you can see, at this frequency, 240 Hz, there is a huge drop in the gain, and at this frequency, for 190 Hz, there is a huge frequency shift. I'm going to skip this. So what we have done was exactly to try to reproduce the flame dynamics at two specific fluctuations. To be honest, you can do in LES, you can do this using both compressible LES approach, but also in compressible LES approach have been proved to be able to compute such a flame response. And in particular, I pointed you out on this very recent publication from the Polytechnic group where basically the two methods are compared. It's an really interesting readings that enlist to all of you the pros and cons of both methods. As we've done before here, some of the details of the calculation of the mesh and of the computational modeling used for the calculation. As for the sepsis limit cycle, first of all, you need to, of course, match the stable flame before forcing. Here I report some analysis of the flame shape without hydrogen. This is a classical V-shaped flame stabilized of the injector lip. When we add hydrogen to the system, something more complex happens. In particular, as you can see, basically the flame is a little bit shorter, and a secondary branch happens here in this zone at the exit of the hydrogen injection. In order to better investigate it, we have used the Takeno index. Takeno index, that is an index that is able to distinguish the regime of the flame that you have analyzed. Analyzing the flame, make use of the Takeno index. What you have is that the methane flame can burn in the mixed mode, while when hydrogen is injected, two diffusion branches appears. One, as I said before, here at the central, at bottom of the central circulation zone, but also one, surprisingly, at the top of the injector lip, which sustain the main flame. When we increase the amount of hydrogen, also a flame lift-off has been also observed, because the higher hydrogen injector will push further downstream the flame. Forcing this flame at the two frequencies that have been highlighted here, what happens? First of all, we investigated the phase average flame dynamics. Here, what you report is basically the phase average flame shape of the reference at pH 10, average over multiple forcing cycle, when the flame is forced at 240 Hz and 590 Hz. What you can see is that together with the flame shape, so the heat release rate, because that's been reportedly normalized, have been also plotted the quick criterion in order to highlight the vortical structure. What you can see is that the injection of hydrogen, so if you can see this point, do not impact the vortex shedded from the injector exit. On the contrary, when hydrogen is injected, the flame shape and therefore the response of the flame to the vortex shaded by the injector is modified. It is because when hydrogen is injected, the flame is shorter. There is a redistribution of heat release rate towards the root of the flame, and therefore the flame roll-up high flame roll-up that you can see here is damped in case of hydrogen. This could be one of the reasons why we have observed in the 240 Hz the drop in the flame FTF gain. The second reason is that, as I said to you before, when hydrogen is injected, the flame is detached, so is a lifted flame now, and therefore also the flame root respond to the forcing, to the acoustic forcing. So we have observed some, especially at 240 Hz, flame root oscillation that here are reported and compared to the experimental observation. This, of course, will change the flame response. analyzing of the two systems at the same times, and what we have observed is that in the reference case, basically flame is always attached to the body. So when forced at 240 Hertz, what is happening is that the interaction with the flame with the vortex shaded at the exit of the injector will elongate the flame, as you can see here, and will generate huge flame, increasing of the flame surface area due to flame tip roll up. On the contrary, since the hydrogen flame is lifted, basically when forced, the hydrogen flame, the hydrogen surface is not increased, but instead the flame is just shifted and translated along the system. This will not generate any increasing of surface area, and therefore the amplitude of the fluctuation at pH 10 is lower, justifying explaining the lower gain observed in when the flame is forced at this frequency. For what concerns the phase shift, that could be definitely explained due to the fact that you inject hydrogen, the flame is shorter, so of course this will lead to a flame shift modification, that is compatible with the variation of the flame length. In conclusion, I was a little bit too long, sorry for that. The probability of LES to end the multiphysical problem, such as thermacoustic instability, has been discussed in this talk. The key message is that if you want to study thermacoustics, you need to use specific modeling, because you need to solve a multiphysical problem. You need to account for acoustic, thermoboundary condition, inlet boundary condition, two-band combustion model. When you introduce hydrogen, you need to take care also of the thermochemical properties of hydrogen. Of course, some improvements are still required, especially for hydrogen, for example, leading to real configuration, pure hydrogen condition, high pressure. I'm going to finish with ongoing projects. At the moment here in Bari, I'm mainly involved and continuing these studies, and I'm mainly involved on experimental numerical study in order to control, to predict and control pure hydrogen flame dynamics, because once you have combustion instabilities, you need to control them. And these activities are still in collaboration with Surfax, MIT, but also other players such as the Combustion University in China. As you've seen, nowadays I also interested in combustion noise problems of pure hydrogen flames. As I said before, instabilities, thermacoustic instabilities are one source of combustion noise, but are not the only one. I'm also involved in some projects such as including ammonia, and this is in collaboration with CNR STEMS from Napoli. Thank you very much. I was a little bit too long, sorry for that, but let me just give a special thanks to the PhD students that performed this work, Dr. Rosnelli and Dr. Agnello, the researcher in Surfax for support, PDP, everything that I know in LES. It's to them, and also I want to thanks people investing time in experiments. MFT guys, Gorkem, Sylvain, Thierry, Laurent. The DLR dataset that have been provided by Isaac, by Janko, because without good experiments, we people that we do LES, we need good experiments in order to validate our models. Thank you very much.
Thank you, Davide, for this interesting and very extensive talk. I think you've been on time. You promised us 50 minutes, and 50 minutes they were. So we have time for we have time for questions. So I leave the virtual microphone to the audience. If there are any questions, raise your hand, and we'll let you ask to the speaker. Okay, if not, I might, okay, we have a question from Pasquale. Sure. Let me see.
Hi there. Sorry.
Please, yeah.
Pasquale.
Sorry for the bad look, but I'm working. I'm working from home today. Thank you, Davide, for the very nice talk. I missed the first part, so if it's something that is related to the first part, please excuse me. I wanted to know if you are looking, maybe it's on your in your last part of the talk. You're also discussing about the sound of hydrogen flames. What are you expecting to be different from hydrocarbons? What are you looking for in this kind of investigations?
Yeah, there are multiple points. It's a good question. First of all, and there is a topic that you know very well. You know that in a hydrogen frame are in some condition intrinsically unstable. So what may be completely different is that an interesting topic to investigate is the interaction between the intrinsic thermodiffusive instabilities with thermacoustic instabilities. This is one point. The second point is that hydrogen flames, as you have seen, are more short, more compact, so they may lead to the onset of instabilities at higher frequency. We have a little bit observed that in the Perkinsta during the talk. So basically, when you have a shorter flame, you may trigger higher instabilities mode with respect to the one that you have in hydrocarbons. Higher modes means that these modes may have some length scale that are more compatible with the flame. So some modeling that have been used in the past on thermacoustics that relies on the assumption of compact flame may not be true anymore for hydrogen flames. So this, in my opinion, are yes, the two direction and the two interesting investigation that the combustion community needs to deal with when for hydrogen flames linked to instabilities and noise generation.
Okay, thank you. Just another side note, the things that you're showing on the right, are you starting to do DNS of this kind of?
Yes, I have a PhD student here in Bari, Francesco, that is connected, and the idea is to start to investigate that. We are not really there, but it's just started, but the idea is to go towards that.
Okay, so looking forward to your results on this. Thank you.
Yes, absolutely.
Okay, we have another, thank you, Pasquale. We have another question from the audience. Johan, please feel free to ask.
Yes, thank you. Thank you for the very interesting and useful talk. I have a small question to the slide 36. You had presented LES with CHD, with the CHD model. Yeah. I just wanted to have a small question. Is it possible to predict the transition? I'm not sure if this, in this case, if it's a bifurcation, but is it possible to predict transition to instability with such an approach? For example, you go from 20 to 50. Yeah.
Yeah, I was not. Yes, you're right. I was not that clear in this. Of course, we did that. So basically, here we started from the stable condition. The stable condition is the one that has been stabilized here. Okay, this is the test case. This is exactly the test point that have been presented before. This is pure methane, 10 kilowatts, stable with CHT. I mean, it's not the CHT itself. This is one point that I would like to point out. I mean, it's the fact that you must have the correct flame shape, because the flame shape will respond to acoustics correctly, and the thermal boundary condition will impact the shape of your flame. So in order to correct the good stability, you must have the good acoustics and the good flame response. This is the point. Then, starting from this stable point, adding hydrogen, and this was done. Yes, I do not have the video, but there is a video where you can see clearly. No, yes, I have it here. It was fast. It was at the beginning of the talk where I presented the case here. So this is a stable flame. The stable flame, when you add hydrogen, you trigger instabilities. So definitely the transition can be predicted with LES if you have the good model.
Yes, thank you.
So here you can see that as soon as hydrogen enters, the correct amount of hydrogen, so the 50% in volume, the instabilities trigger itself automatically.
Thank you so much. Yeah.
Okay, are there any questions from the audience? If not, I have a question probably related to this last point that you said. You know, you showed that LES it's a powerful tool and can be quite accurate in predicting thermacoustic instabilities. My question is, on the practical side, industrial side of things, do you think that industry will use LES for design purposes, or we will need to rely on like lower fidelity models, low order models to
absolutely.
can initiate the advancement,
Depends a lot.
Promote the use of hydrogen in industrial system or in gas turbines.
Yeah, absolutely. It's they needs to use the two. I mean, it's not reasonable to say in a design phase perform 100 LES simulation. It's not possible. You definitely need to perform a couple of good simulation in order to have, for example, the good flame response, the good flame transfer function, flame describing function, what we have done for the Miradas, and then use that transfer function as an input in low order modeling, acoustic modeling, where it is more easy to change geometry, length, acoustic characteristic properties, and that in a design phase. When the design phase is finished, of course, LES could be used to validate or optimize. My idea is that all the tools need to be work together in a synergistic way. I mean, make full use of the advantages of all tools. But LES is the tool to understand physics. Okay, if you want to understand what happens, what really happens, you need LES. Because also, I mean, a validated LES, you have access also to a series of fields that I showed you before. DMD, you can understand the coupling between the equivalence ratio fluctuation and the pressure fluctuations. I mean, it's a really powerful tool because you have all the information there for you. It is just up to you to exploit and find your answer.
Okay, thank you. I think on this note, we can end the Q&A session, and we thank the speaker again. Thank you, Davide, for your talk, for for saying yes to our invitation. We are glad to have you, to have had you here in this lecture series. Okay, and so yeah, we can conclude this event today, and I will see you all, and next week there will be another lecture, and so I hope to see you everyone at the next one. And thank you, Davide, again for your talk, and see you.
Thank you again for the invitation. It was a pleasure.
Have a nice weekend, everyone.
Thank you. Bye.
Bye. Bye.